Okay, so here's for an optional extension of section 11-4 on ANOVA. Just in this part 2, dealing with the actual calculations of an ANOVA with sample sizes being the same. So again, this part's an optional extension if you want to learn more about ANOVA tests. And then, so calculations when the sample sizes are the same are complex, but totally doable. And calculations when the sample size are different are not covered in this course or in that textbook, and they're also a bit complex as well. By the way, both calculations use the F distribution, which is now provided on Canvas, also on that YouTube and other tools page. If you just scroll down to tables, you'll see F distribution there. And it looks like this. There's a fair few pages to it, or just a few more than the other tables, and I'll show you how you can use it. Alright, so just for doing the actual calculations to find the F test statistic, if you're going to calculate it, keep in mind it's still the variance between samples divided by the variance within samples. Now, this is what the actual formula looks like, is F test statistic equals N variance of X sub bar and variance P, which what that all means is the numerator is the sample size, N, times the variance of the sample means. So that's what this S squared and then sub X bar means, is the variance of the sample means. And this one, S squared sub P, is maybe not the best variable choice, but it's the mean of the sample variances. And keep in mind for variance of means in ANOVA, we're going to use the variance equal to the sum of all the values minus the mean squared divided by n minus 2, which usually it's n minus 1 for a variance, but for ANOVA tests, if you want to do this calculation, use n minus 2. Alright, this is an example that's pulled out of later in the textbook in this section. So essentially there's 3 samples here, all of them have sample sizes of 4. And then in this first sample, the mean is 15.5, second sample 6, third sample also 6, and then the variances between the samples are 3 for 1, 2 for 2, and 2 for 3. And so all of these have roughly equal sample variances, and so I'm satisfying all those requirements from before. Now, to do some of the calculations, so the mean of the sample means is 15.566. It comes out to 9.17 roughly, which really it's 9.16 repeating. And so I found that just because I'm going to use that in this calculation for variance, because I'm taking the variance of the sample means themselves. So I'm doing the variance of these 3 sample means, treating the sample means as like their own data set and finding the variance of that. So then I plug in that 9.17 into that actual variance formula and such, where I'm taking every mean, subtracting the average, squaring that difference, adding all of that up, then dividing by each of their sample sizes 4 minus 2, which should come out to about 30.083 repeating. The more I keep going with that is next I find the mean of all the sample variances. So the sample variances were 3, 2, 2. And so just finding the mean of those 3 variances comes out to 2.3 repeating. So now when I calculate the actual F test statistic, I'm just plugging everything into this formula here. So now just sample size 4 times that variance of sample means, 30.083, all divided by that mean of the variances should come out to 51.5721. Alright, so that's the test statistic, and if we want to conduct an ANOVA test with the traditional method or the critical value method, next we'll need to find the critical value using the F table. And so there's 2 separate degrees of freedom we need to look at for using the F table. There's enumerator degrees of freedom, which you find from k minus 1, where k is the number of samples. Then there's a denominator degrees of freedom, which you find from k times n minus 1, where n is the sample size. That's the same between the 3 between the samples. And so in this case, K is 3, since there were 3 separate samples, and N is 4, since all of them had a sample size of 4. And once you plug all that in, the numerator degrees of freedom comes out to 2. Then the denominator degrees of freedom comes out to 9. So when you look at the F table, there's 2 pages with the degrees of freedom, or sorry, and significance level of 0.025. Then there's 2 pages with a significance level of 0.05. So if, say, I'm using a 0.05 significance level, then again, my numerator degrees of freedom was 2, and my denominator degrees of freedom was 9. So then I just see where those two meet up. So numerator degrees of freedom 2, denominator degrees of freedom 9. And I would know that the critical value in that case is 4.2565, which is what I have here. Then if I wanted to use a 0.025 significance level, I just have to look at the 0.025 pages. Same numerator degrees of freedom 2, denominator degrees of freedom 9, and that critical value is 5.7147. Which is right there. Now, since ANOVA tests are right-tailed tests, for either significance level, the test statistic is bigger than the critical value, which would imply to reject a null hypothesis of equality. And you could still find that same conclusion if you plugged everything into technology and found the p-value, which would come out to 0.000018, which again is incredibly small, which would be much smaller than either 0.025 or 0.05, both of which would imply to reject a null hypothesis of equality. And if you want to read over this more in the textbook as well, you can start on page 586, is where it starts discussing some of those calculations. And just some other extension notes here. So, for when you design the experiment of an ANOVA, just some things to keep in mind if you want to make an ANOVA good, basically. Is when performing an ANOVA test, we use one factor as the basis for partitioning the data into several categories. So just one factor to separate the different samples. Then if we conclude that there's a significant difference among means, we can't be absolutely certain the differences are explained by the factor being used. We would just know that the means would not be the same. And so just ways you can minimize errors is one way is to reduce the effect of extraneous factors is to run a completely randomized design, which is really good for any kind of statistical test, in which each sample value is given the same chance of belonging to different factor groups. And another way to reduce the effect of extraneous factors is to use a rigorously controlled design in which sample values are carefully chosen so that all other factors have no variability. And again, both of these are good things for any kind of statistical test, really. Alright, and that's just some quick extension stuff if you want to learn a little bit more about how ANOVAs are done.